Yeah, we always typically use P there, and I'll go ahead and do that as well, just so we're consistent. Okay, so that's an important model. Now that's very, very basic. Let's see what happens with an investment if you are given the interest return more frequently than just once a year. This has been called compounding. Okay. Compound interest. And oftentimes we let the letter N represent the number of times you're going to get the interest each year. Number of times per year that the interest is earned. So let's play with that for a second. Probably one of the most common that you see, like with a car loan, things like that, is monthly return, monthly compounding. So if you have monthly compounding, then N is going to be equal to 12 times per year. If you have daily compounding, N is going to be equal to, oftentimes they round off, even though our calendar is not precise at 365 days per year, they oftentimes use 365 if you're doing daily compounding. That means you get your interest every day. Now, are they going to give you, let's say we have a 6% investment where that's the annual percentage rate. Let's stick with APR is equal to R, which is, let's stick with 0.06 in our example. Are they going to give you 6% every month? No, that doesn't make much sense. I mean, I would jump at that if they give me 6%. Or matter of fact, if they give me 6% every day, I'd even jump. I'd jump at that real quick. That would be almost like something illegal, probably. Okay, right? Everybody agree? So how much are they going to give you, say, every month? Wouldn't they give you only a 12th of your annual percentage rate, or 365th of your annual percentage rate every day? Okay, so what you're going to be getting typically is R over N, for each compounding, for each time you're going to get your interest earned. Max?
Well, actually, isn't the more times you do it, the more money you make, assuming you have the same division of
Same interest rate?
Same interest rate per year.
Yes, you are going to make a little more. Now you think you're going to make a lot more. Like if you go from, say, monthly compounding to every day,
yeah.
But what's going to happen is the amount of interest that you're going to earn for each of the periods, each of the pay period, or each of the earning periods is going to become less and less. And because you're going to be getting, okay, so here's the story. The money's going to go into the investment after a period, right? And so you're going to get a little bit of interest added there. So that chunk of money now has the interest as part of it. Now the interest, that total amount now is earning interest during the next period. So the more times you compound, you're getting a little bit more bang for your buck, essentially.
But credit cards are usually the daily, and the CDs are usually the simple, right? I mean, because I think credit cards are usually daily.
Yeah. Well, now, and of course, that's a debt. That's something you
right,
owe.
That's what I mean.
Typically, which you get in trouble with frequently. Okay.
Right.
But I'm trying to stick with the investment thinking because that's a little easier for us to understand at this point. Okay. But that's true. Oftentimes.
Banks always benefit themselves.
Oftentimes, if you take a chunk of money and put it into a credit union or something with a certificate of deposit, they oftentimes will say you just have to leave that in, and we're going to give you this annual percentage rate, and you've got to leave it in for say 2 or 3 years, and it's going to be an annual percentage rate. They may not compound daily for you. Depends on how the contract is written. Okay.
You also get higher rates for putting in
Yeah.
Like there's a big difference between 5 grand or 10 grand for the interest rate that you get.
Yes, yeah, they're
Huge.
willing. Financial institutions typically are willing, if you're gonna hand them a larger chunk of money, they're gonna give you a better rate of return because they have more capital in which they can then take and go out and invest that. So they're willing to pay you a little higher rate of return by you giving them a bigger chunk of money, okay? And once again, as I've said previously, that's part of the reason that folks that are wealthy get wealthier and people that don't have much to invest kind of stay with a small amount available. Okay. So what we're going to get here is we would have our 6% divided by 12, and that turns into 0.005. Notice that that is a half of 1%. Everybody see that where the decimal is here? That's a half of 1%. 1/2 of 1% is what that means. And that's what they would give you every month. If you were doing it every day with your R over N calculation, that would be 0.06 divided by 365. And if somebody punched that on the calculator, the reason I picked 6% was because I knew on division by 12 it would reduce nicely. But on this daily one, somebody just punched 0.06 over 365.
0.0017.
0.0017.
Hold on.
It's not that hard of a calculation. Let's go fast.
I missed the number. 1.6438.
No, it's
No?
no.
To the
Point-
negative 4, 10 to the negative 4, that's in scientific notation, so it's 1.6438 to the negative 4, so it would be,
Oh, to the -4. Yeah,
Right.
this seemed mighty high to me. Okay. How many zeros? Okay, tell me in
3.
scientific notation.
1.644, and then times 10 to the negative 4, times 10 to the negative 4.
times 10 to the -4. That's
Yes.
scientific notation.
Yes.
That means this is a small, when you see a negative exponent in scientific notation, you're
Going back.
driving this number smaller, not larger, smaller. So this is gonna be 3 zeros, 1 6. Okay? So you can see that this is clear, this is way down. This is about 1/100th of 1%. Very tiny amount each day. Very tiny amount each day. Okay, I don't want to spend all day just fiddling with this. I want to kind of get to where we're trying to go with this. So, we have our basic model. So what happens is our future value becomes the initial value, the present value, times 1 plus, what would you think it's got to be for your rate of return for each period?
R.
Not just R,
R over N.
R over N, and then we're raising this now. This is what you're getting. This is the 1 point, it could be like 1.005, right? Right here. And you're raising that to the total number of compoundings that occur. The total number of compoundings that occur. If I was doing this monthly, then my exponent here would be a what? 12.
12T. If it's
Well,
only 1 year, it'd be
For a
12.
year, yeah, it'd be 12 at the end of the year, wouldn't it? If it was the end of 2 years at monthly compounding, it would be 24, wouldn't it? You'd be getting 24 hits on your money. Make sense? So what the exponent becomes in general then is that number of compoundings per year times the number of years. That's equal to the total compoundings right there. That's the total compoundings that occur. Now we'll do something with some numbers here in a second. So if this was 12, and you left it in for 2 years, you'd be getting 24 compoundings. If it was 365 daily compounding, you'd be for 2 years, you'd be getting 730, isn't it? You'd be getting 730 compoundings. Make sense? So here's the general formula right here for compound interest. Compound interest. You want to memorize this one. It's not a hard one. It's something that comes up over and over and over again. Okay. Any questions so far? Okay. Now, I wonder what happens if we start letting the compoundings go even more than daily. What if we said every minute, every second? Instantaneously, we're going to give you some interest. Look what's going to happen to your interest rate over n. As n goes towards infinity, we've been doing some of this back when we did rational functions, right? And we're talking about n behavior frequently. So as n goes towards infinity, this number r over n is getting driven towards 0, isn't it? But it's slightly positive, isn't it? Being driven towards 0, but slightly positive. And look at what happens to that exponent. Okay, so this base right here, isn't this a base? Okay, so this model is turning into, look at what's happening now to a. Let's see if I can write that in here nicely. A is then approaching the initial value times 1 plus a number very close to 0. And let me erase this. Okay, number very close to 0. But look at the exponent if we're letting n go towards infinity.
And that gets very close to infinity.
Yeah, that's blowing up on us, isn't it? So nt, the product nt, is heading towards infinity as well. So we're ending up with something that's kind of strange. Kind of strange. So we have a number, the base is getting driven towards 1, while the exponent is blowing up. Now that's a fairly sophisticated idea. And so at this level, you're not in calculus yet. So at this level, the best way to interpret this is to look at a table of values of how this thing gets driven, how it gets driven. So what I want to do is I want to take just this part of it right here, and I want us to build a table. So let's let R equal 100%. So let's say we're getting 100% rate of return. We would like that, okay? We're getting 100% rate of return annually, and we're going to just leave it in for 1 year, t equal 1 year. That's going to make our equation a lot simpler. And what we want to investigate then is what happens to that expression that's in the parentheses in our formula here with that exponent. So this is going to become 1 plus, and 100% is what as a decimal? Very good. It's just 1, isn't it? Okay. 1 over n raised to the n. 1 plus 1, 100% rate of return over n raised to the n, and we're just going to be talking about what happens after 1 year. We want to get a handle on this. And what we want to do is we want to see what happens as we let n grow. We want to see what happens to this thing. Where does this head towards? So we'll let our calculator do the work for us. Now in our calculator, our unknown, here we're talking about it using the symbol n, but in our calculator that must be what? X. So what we're going to do is I'm going to stick this into the y equals screen, and then we're going to go ahead and build a table of values and let this n grow. So we'll come over to the calculator. And we'll go to y equals, and we're going to take this expression in parentheses, 1 plus 1 divided by x close parentheses, and raise that to the x power. So here's a function stored in the calculator. And now what I'm going to do is I'm going to go on your window key. On your window key next to y equals, you'll notice there is a table set button. Table set. So we're going to activate table set, and we're going to let this start at 0. X or n equals 0. And then we're going to let the table jump or change the n value. Let's make it every 10. Every 10. And now, over on your graph key, if you use your second or shift key, you can see that on the case of the calculator it says table. So we go shift, table, and it generates a table for us. And why does it give us an error if x is 0? Think of the equation we're modeling here. As Max said, we can't divide by 0. So at 0, we have 1 plus 1 over 0, and that was causing the thing to be undefined right there. Okay, now, however, if the number of compoundings is 10, you'll notice this value over here, 2.59. And look at where this is going. 20 compoundings, 30, 40, 50, 60, 70. I can just keep going down. Is it blowing up on us? No. Where's it heading? Are you getting excited? You should be. What are you seeing, folks?
It's growing.
Yeah, that's cool. We like it growing, but where's it growing towards?
Infinity.
Let's see. Look at the change. Look at the change that is occurring in y here. This is a 10,000th change, roughly. Here's 2 10,000ths. Okay? It's kind of, doesn't it look like it's kind of settling in? Is this a familiar number? Thank you. I've been waiting for somebody to say that. E. It's approaching E. Very interesting. Let's go back up on the board. So what that's telling us then, this thing is approaching E. If the percentage rate is 100, then this base here, this thing that I'm going to call the base, that's just going to be a number. It's approaching a value of E. I wonder what would happen if this R was something else, like 6%. If it was 6%. So let's take and give me a little more space on the board here. If I let R equal 6% or 0.06, then what we're going to look at as we let n approach infinity is we're going to be looking at 1 plus 0.06 over n raised to the n power and see where that goes. And that's a real simple change in what we just put into the calculator. So I come back now and I go to y equals, and I just come in here, and instead of a 1, I insert. I go into insert mode, watch the cursor change. I shifted, and I go insert, and I'm going to put 0.06 right there and delete that 1. Okay, now I'm going to go back to the table and see what this looks like it's homing in at. Look at that. Looks like at 4 decimal place accuracy with 420 compoundings in a year, it's homing in on this value of 1.0618 approximately. 1.0618. Now, let's go back on our calculator. Let's get out of the table, back on the home screen, and punch this, E raised to the 0.06. E raised to the 0.06. There you are. So by a numerical investigation, and this is not a formal mathematical proof, but by an informal numerical investigation, it appears that this expression, as n goes towards infinity, if the number of compoundings goes towards infinity, the value you get for that thing is approaching e to that 0.06 power. Or in general, it's going to approach e to the r. E to the r. Later today.